Okay, welcome back. So this is the supplementary video for the example number 3 that we didn't do in the lecture. So just to supply you with the solution here. Yeah, so this is pulled out of, for your reference, is pulled out of from your lecture notes, chapter 8.3, question 3. Okay, so it's put under the Fourier transform chapter, but it's also PDE. So this one, it's a little bit intended as a transition from the Fourier transform chapter to the PDE chapter. So I would don't feel too bad if you cannot do this on your own right away when you finish your Fourier transform chapter. But you're expected to be able to do this after both the Fourier transform and the PDE chapter, right? So it's a little bit just ahead of where you are, but since it's technically doable, you'll understand all the steps as I go through it with just the Fourier transform techniques. So I decided to include it as a transition example as well. Okay, so just to repeat, you don't expect to be completely do this on your own right away, but you will after the PDE chapter. Okay, but mainly it's to see how Fourier transform works for PDE. Okay, so this is the problem. We have a PDE of a function u of xy, right? It could have been f, but we'll use u. So before we do the method, let's understand the question a little bit. Visualize the question first to see what it's asking, right? So first of all, look, this is a notation that is not the most transparent. Usually it's nicer to write in partial derivative. But once you get used to it, it's fine. But at first, if you feel uncomfortable with this double x double y notation, write it in partial derivative first. So this is taking the x derivative twice. So it means this, and taking the y derivative twice on u equals to 0. So there's a name for this, right? This equation is called the Laplace equation. So so we are trying to find u of xy, okay? And the question in your notes is a little bit more explicit. It says find u of xy as a real integral, a real infinite integral, okay? So we don't expect to find this multivariable function. It could have been f, but we were going to use u. U of xy, so we will plug in x and y, so the domain is not just on the real number line, but it's the real plane. And we don't expect to find it as a nice little function. You can write it out, but we expect it's an integral, okay? But we also want, it's also an infinite integral, so you expect the limits to be from minus infinity to infinity, but you also want it to be real, so you don't want any complex numbers in it. Okay, so this is the canonical example, a very typical example of PDE, the Laplace equation, and you'll see this over and over again. But what makes the answer different is the boundary conditions. Okay, so the PDE itself is very boring. I mean, it's the same one after another, but it doesn't mean the answer is the same because of boundary condition. Just changing the boundary condition a little bit, you get a completely different answer, even if you have the same equation. Okay, there's a deeper insight going on over here. It's, for example, the wave equation. The wave equation is just a master equation that governs all waves. But of course, if you look out in our world, different waves behave very differently, right? And the reason is because how it reflects off the wall, how you generate it, right? So it's the initial condition, the boundary conditions make the waves very, very unique. So that's the similar idea. Okay, this is the Laplace equation. Okay, so that's the first thing you understand here. The next thing is to try to understand domain and then understand the boundary conditions. Okay, so the domain here we are concerned about is what's usually best is plotted out a little bit, right? So y goes from 0 to 1. So this is the domain. Normally, in single variable functions, you plot x and fx like this, but now we have two variables. So you have x and y, both are the domain. So I don't only plug in x values, but I plug in any values like this, a certain value of x, a certain value of y, a certain value of x and y like this, and you should get a value of u of xy, right? So in some sense, it's like a third axis that comes out. So the domain is 2 axes, and the graph is 3 axis. So every point you want to have an extra axis that comes out u of xy, right? So that should be perpendicular to both. It's difficult to draw on a 2D surface. I could probably draw it in a more typical 3D way, but you get the idea. So every point on this domain, right, there's a value of u of xy. So basically, this doesn't plot out a line, but it plots out a surface, okay? So we're trying to find a surface, but do we want the whole xy? No. Just hit it up there. We want y to go from 0 to 1 only, and x to go from -infinity to infinity. Okay, so what we want is this part, all the xy input here, and we want to find, so for all x and y input over here, we want to find the surface that goes on top of it. So that's the domain we understand over here. Now the boundary conditions, okay? So at y equals 0 and y equals 1. So we're telling us y, so it's telling us y equals 0 is over here. It should be 0, okay? So the value of the function along here is going to be 0. So imagine the surface, it's going to fall off and fall to 0 over here. It's like, think of a bed sheet, and you're tugging one side of the bed sheet into the mattress, and you can flop and do whatever you like for the rest of the bed sheet. Imagine a flat sheet on and just wiggle it, but the other side on here has to be 0. So there's no fluctuation at all. One side. How about the other side? We want to constrain that as well. The boundary over there, it's e to the modulus of x, or absolute value of x. How does that look like? Well, e to the minus x looks like this, right? The absolute value just means whether it turns this into an even function, where if you change x from positive to negative, it should behave exactly the same. So it mirrors it over here, like this, right? So this is e to the minus absolute value of x, okay, right? But how do we apply it over here? Well, u at y equals to 1. So u at y equals to 1, I need to plot a third axis, remember, but I'll sort of take some liberty over here, right? So this is u of x, and y equals to 1. When it's constrained at y equals to 1, it's e to the minus x like this. So it does, the x value just goes into here, but y has to be 1. So imagine the bed sheet tucked into the mattress again. One side is firmly tucked into the mattress. The other side, you're making this little tent on the other side of the mattress. And then in the middle, it can fluctuate however it likes, okay? All right, so, and we want to find out how it looks like in the middle. If I constrained it like this, and it's given this constraint, okay? This is how it evolves in the middle. Okay, there's more physical applications like heat and wave like that, but we'll work with this. Now, finally is x goes to 0 as x goes to pi is infinity. So what we're doing here is we need to define the boundaries. What is u doing? What is the function u doing at y equals 0, at y equals 1, x equals minus infinity, and x equals infinity, right? So we've done these two, the boundary conditions for these two. And how about the boundaries for these two? Well, when x goes to minus infinity and plus infinity, we just wanted to go after 0, okay? A lot of the times these waves, the volume or the area under the surface actually have some physical representation, physical meaning. Maybe the amount of energy, you're talking about the amount of energy stored, like that. So you kind of don't want it to not go to 0 at infinities, because then your area under your volume under the surface will be infinite. And for example, if this is a probability density function, then your probability will be infinite, which is not normalizable. Okay, so those are physical applications. This is a very just to tell you, this is a very common boundary condition. So, okay, once more, it goes to 0 here. It goes to 0 on the edges at infinity and minus infinity. But this side, it's like this. We want to find out how does u look in the rest of the domain. Okay. All right. So that's how we want to understand the problem first. Okay. Now, how do we solve it with Fourier transform?